Just as
Yes. Okay. Hi, everyone. Good morning, and thank you for being here on Reading Week. My name is Parnas. I'm your TA. I'm the one marking your assignments, and today we'll be covering an HFSS tutorial. So if you open HFSS or launch it from your desktop, Mac, or whatever you have, and then you would see this environment. So hopefully you're familiar with it. If not, don't worry. Today we are just going to, I'm just going to be the one talking, and then if you have questions, you can ask, obviously, but you have time to go home, practice everything that we talked about today, and then come back tomorrow and ask questions. Okay. So let's say you want to start a project in HFSS, so you launch it like this and would actually open. So let me go back here. It would actually open a project for you immediately. Here, this is mine is 2020. You might have 2021 version. So, but the whatever you do here is no different. So as you can see, it opens a new project for you. If you want to create a new project here, you can also do that and like have two projects in one environment open. So for example, project 5 is the one that was automatically opened or created. I can go and just create another project here. I can even rename it or delete this project. So if you right click on project 7, you can completely delete it. So that's it. Now let's say in project 5, I want to simulate some antennas and I want to basically analyze different structures. So usually for the projects we use, you go right click, insert, and then insert HFSS 3D layout design, or sorry, HFSS design. It's taking some time. Yeah. So we went with HFSS design, the first one. Now you have this 3D model here, as you can see. Maybe we can continue this after the class. So we have this 3D environment where we can basically make our structure here, the 3D structure that we have. And then like any Maxwell equations, when you try to solve it, you have to have excitation, boundary condition, and obviously the geometry, right? So we go step by step, assign these different components of the project so that Maxwell's equation can be solved for it. Okay. So now let's say I want to design a very basic half-wave dipole. As you know, a dipole is two conductors, and then in the middle we have excitation, right? Or two cylindrical, basically, structures. So for example, here, first thing we want to do is have a little cylinder here. So, sorry, this is basically, let me go back. Yeah, these are all the 3D models that you can draw, and these are the 2D models, like surfaces that you can draw, right? A cylinder is a 3D shape. You have cube here, you have something called cone here, cylinder, sphere, and then even like polyhedron, for example, that you can draw in 3D. Now, for a dipole, it's simple. We just want two cylinders. So what I do is I will draw, this is one of the cylinders, right? This is the other one, the two conductors. And then here in the middle, I have the excitation, right? This is the dipole. So simple. We know this is PC or a metal. this is a metal to PEC. So for easier simulation, we can just assign, is that my phone? So for easier simulation, you can always assign perfect electric conductor here because HFSS know inside a perfect electric conductor, E field is 0, right? So it will make it faster to solve this problem. You can also go with a realistic one. Let's say you have 2 cylinders and then you have metallization. Look, actually metallization, like copper, things like that. But because copper is not considered, like it's going to be a realistic case of copper, it tries to solve here as well because E is not exactly 0. It's very close to 0, but it's not exactly 0. So it would take time to solve it here. Now tell me, like, how are we doing? Am I going too abstract or is it, you've seen a dipole in the course, right? Okay. Okay, so this is the problem we have. Let's say for easier case, and this is what you should do actually. So when you're designing an antenna in HFSS, always try to go with something that would take less time to simulate, right? We'll talk about it in a planar structure as well. But it is, as I said, it takes less time to simulate this, so you can easily simulate it quickly. And then if things are not going your way, you can adjust the lens, the different parameters to optimize it, and then apply the realistic cases, right? Okay, so what I'm going to do here, there are 2 ways to draw this. Either I can have a cylinder up here, a cylinder up here, right? Draw 2 cylinders. But another way for me to do it is just have one large cylinder and then define a gap cylinder here and subtract this from the main cylinder. So both ways is okay. But one thing you have to keep in mind is that you try to do all of this using parameterizing your structure so that when you want to tune or optimize this structure, it becomes much, much easier. These are basic things. I know as grad students, you already know this, but I'll say it anyway. So for a dipole to work, we have this radius that is very small compared to the length of the dipole, right? And then we have the length of the dipole here. What else we have? We have the gap size here. I can call it G, right? What else? I think that's it, right? Okay. So let's design this. I'm going to put Z0 here, ZL2 here. This is G2, right? And then the radius is R already. Okay, so let's draw this, keeping this coordinate system in mind. Okay, so back here, I'm going to do what I said, basically. So I'll just draw a random cylinder here, and then I come here and edit it. So the cylinder was made, cylinder 1. I can even call it dipole. I can go here on this box, double click. I can call this dipole. Again, when you have a lot of geometries in your structure, it makes it much easier. Later, if you call things rectangular 1, 2, 3, and then you try to change things, you have to go click one by one to see which one is what, right? But if you give them meaningful names, then you know that dipole is that one, you go immediately change it. Now, this cylinder, a material is assigned to it. So you can go change the material. For now, automatically or by default, vacuum is assigned to it. But we want to change it to PEC. So I'm going to search here PEC. PEC is found here. I'll just assign it like this. I can even change the color here, make it look like metal like this. I can even add transparency to the structure, or I can show only the wires or the, what do you call this? The wires or the boundaries of this shape. So anyway, these are just, if you want to make nice pictures for your papers or your reports, you can do that. So now this is the appearance of the shape. Now let's go parameterize this thing. When you are trying to change the properties of the shape, the geometry, you go on the second one, the yellow thing, to change it. Okay, now the central position. So as I said, the cylinder, the main cylinder is going to go from minus L2 to L2, right? And the center of the surface, the cross section, is going to be at 0, 0, 0. So 0, 0, 0 is fine. The radius, I'm going to add to it R dipole, radius of the dipole. I can even like add underscore here. The height. So it asks every time you define a new parameter, you try to move on, it says like, what is the value of this parameter? So R dipole. Now, another point is that now you have to decide for these parameters, right? So let's say I'm trying to design this at 10 gigahertz. So at 10 gigahertz, a half-wave dipole is 10 gigahertz. Then if you're trying to find L, which is equal to lambda over 2, then you have to find lambda first, right? What is lambda? So 300 over 10 over 2, that would be, this would give you in millimeter lambda, which is 30 millimeter. And then over 2 is going to be 15 millimeter, right?
Yeah.
So that's going to be approximate length of L. Is this going to give you exactly what you need at 10 gigahertz?
Exactly. No, into cut a little bit.
Yeah, why?
Because edge effect.
Fringing fields of from the edge, right? Okay. So anyway, the first calculation, rough calculation, it tells us that L, if the dipole length is 15 millimeter, it's almost lambda over 2 at 10 gigahertz. And that would mean that this would resonate over, it would have the input impedance of how much?
78.5.
Almost 75 or 70, something like that.
Yeah.
Oh, right?
Yeah.
Okay. So this is what we know about the dipole. Now let's do this. So for radius, I know if R is way less than L, then I'm okay. This is going to be considered a dipole. So if this is 15 millimeter, you can go to 1.5 millimeter, 10 times less. You can even go to half millimeter, it doesn't matter. Like the less you go, the smaller you go, the approximation is better to make it a dipole. Okay. What else?
Yeah. What about the radius? What's the radius you want? For the
Yeah, that's what
wire?
I'm saying, that the radius must be smaller than L, right?
Okay.
Much less than L, which is 15 millimeter. How fast am I going? I tend to go fast. You're good? You're good? Okay.
But can you make the screen more visible, because it's, I don't know.
More visible. Oh, yeah, I can do that. Then this one has my screen. Is it better? Yeah,
Yes, that's fine.
I don't know. You said the quality always is like this.
I don't know if everybody else is able to, it's not even legible.
I don't know how to change. Is it because of this? I don't know how to change the quality, sorry. Okay, but here, let me point to things. So here it says command, the create cylinder. Here the coordinate is global. I'll explain this as well. Now we have one coordinate system, which is the global coordinate system here. If you had, now it doesn't let me change it. If you had another coordinate system defined, you can even create shapes in that coordinate system. I'll explain it. Anyway, and then, so our dipole here, the center position is the center position of this cross section. since we're considering the cross section to be in the center exactly here, it's going to be x, y, x, y, and then z, right? So the center would be 0, 0,
0.
z, 0, right? Then we have axis, which is like, where is your cylinder aligning with, or where is the length of your cylinder? And I chose Z because I'm going to lie this cylinder on Z axis. Radius, our dipole. So let's go with 0.5 millimeter. Then height, let's say L dipole, parameterize it, and then that would be almost 15 millimeter. So let's say, okay. Oh, something else. Height, okay, sorry about that. Yeah, so this one, I forgot that HFSS, it starts from one point, unlike CST basically. It starts from one point and goes on based on the length here. It goes up, right? If it's a positive number, it goes up. So what we gave it actually, we said start from 0, 0, 0, go up with this 15 millimeter, right? You can change that and say it starts from minus L dipole over 2. And then say, okay. So now the dipole starts from minus L over 2 and goes up for L dipole. So that way it lies from minus L over 2 to L over 2. Does it make sense? You can always, like, if you forget, like me, you can just go back and change it. Now let's go to subtract that gap in the middle. So we need another cylinder. I'm just gonna make another cylinder here. Then do the same thing for it. The only difference is that here, my cylinder starts from minus gap dipole 2 and goes up to gap dipole, right? So here, the center position it asks, I'm going to put gap dipole over 2. Again, the axis is Z. Radius, I'll just put 1 millimeter here. Radius is going to be R dipole again. Height is going to be gap dipole, right? Let's say I chose this gap dipole, right? I gave it a random number for now. Let's look at it. It's here, right? Now I looked at this stuff and I think like this gap is too large. I want to change this parameter. How can I change the parameter? So after assigning a value, if you decide to change the parameter, you can always go to HFSS, design properties here, and then here you can change everything you want here. Now I'm going to put about 0.5 millimeter here. Look at it again. Okay. Now, if I subtract these two geometries from each other, I can call this gap. And the dipole would be created. For subtracting, first you want to assign, or you want to select the geometry that remains, and then the second geometry would be the one that is getting subtracted. So you go dipole and then gap. You can hold on to control and then choose gap. Then we go to operation here. You can see in operation, we have all kinds of things or translations or transformation that you can do on the geometries. You can move a geometry, rotate it, mirror it. You can add and mirror it, or add and move it, add and rotate it, add and mirror it, and then unite, subtract. We want to subtract this here. The first is the first one, it says blank parts and then tool parts. That means that the part that is getting remains the first one, and then the second one that is getting subtracted from it. So if I do this, then it gets subtracted. So if you look at it now, you have this option from orient to look at different views, basically. Okay, so we managed to create the dipole. This is the geometry. The geometry is done. Now what else we need? You don't know, let's say you don't know what you need, right? You go here, simulation validate. It says your 3D model is something wrong with it. Good. Then boundaries, you don't have boundaries in excitation. You don't have analysis set up, right? So let's go and check all of this. What's wrong with my 3D model? Oh, this is because, yeah, we haven't assigned a boundary. Okay, so now this dipole is in vacuum, right? We want to say that this dipole is going to radiate. So in HFSS, whenever you want to say something is radiating, you put a box around it or a sphere or something that says, this is the boundary that things are not going to reflect back from it. It's just going to capture the radiation, right? It's not like a wall or mirror or metallization. This would define the bound that the dipole exists in it, and then it's radiating. So how do you define that? So the simplest way is to define this. I'll show you, go back to draw. Let's define a box around this dipole. Again, this is something that you can choose from here. Then in this box, HFSS roughly say that you have to be about λ/4 from your geometry for this radiation box to work as you want. Okay, so in X, for example, we have our dipole, right? We want to be away about λ/4 from this our dipole. So we say our dipole, or you can define basically length of air box in X direction, let's say, again, starting point from -2, minus L air box in X direction over 2. Then we have L air box in Y direction over 2. Then we have L air box in Z direction over 2. So whenever you have a rectangle, you can just say, parameterize it this way and then define the length on that direction. This is basically what like this. This is X, this is Y, this is Z. Let's say you want to define cube here. You define one of the points, let's say here or here, doesn't matter. Then you define the length alongside it. So this is Lx, this is Ly, and you want to define it symmetrically, Lz, so that the center of the box would be at 0, right? You define this as minus Lx over 2, then go Lx. Then that would mean this is Lx over 2. So you see, in X direction now, this box is at the center. Again, this point, if you start from minus Ly over 2, go Ly, then that means that this point is going to be Ly over 2. So again, symmetric in Y direction. So, okay, that's why we define it this way. Now it asks for L air X. So we said, in X direction, our geometry goes from 0 to our dipole. We want to be about λ/4 further away from that. So we say air dipole plus λ/4. Now it says, what is lambda? We already calculated lambda. That's 30 millimeter. LRY, again in Y direction, again, we have our dipole plus λ/4. LRZ, now in Z direction, we have L dipole minus L dipole, right? We want to go λ/4 from this one. So LRZ is actually going to be L dipole plus lambda over I think I made a mistake here. I'll show you. X. Then the length, we just define it as we parameterized. LRY, LRZ. I'll show you what's the mistake. Now this is for the geometry or the radiation box that you want to define. It's a good idea to make it display wireframe so that you can see inside it. So now you see, this is the box. Since I said LRX is going to be, LRX is basically the total length of this one, right? If we are away about lambda over 4 from this side, lambda over 4 from that side, right? So that the total of that length must be lambda over 2. And then air dipole must be twice because we are going diameter of that dipole. LRY, the same thing. So we have 2 multiplied by air dipole. The length of the dipole to be the length of the radiation box. Yeah, we want basically, let's look at the cross section here. This is the box from the top, right? X, Y. Now the cross section of the dipole is like this, right? Now the radius is R dipole. I call it R. We want this, the distance between geometry and the boundary of the box to be lambda over 4 away from each other. The same thing on the other side, R lambda over 4 at least. That means that L air box in total, Lx of the air box must be 2R plus lambda over 4 plus lambda over 4, right? Yeah, sorry, I didn't explain it well at the beginning. And then the same thing in Y direction. Now in Z direction, the geometry ends at L over 2. The total length that we have is L. We want lambda over 4 here, lambda over 4 here. So that means that the total is going to be L plus lambda over 2 in Z direction. Now look at it at the length. This is the dipole. You have L here, the length of the dipole, lambda over 4, lambda over 4, right? So the total of LZ air must be L plus lambda over 2. Does it make sense? Okay, so this is what the air box around it would look like. Now, let's go back to simulation. Look at this. Now it says the 3D model is okay. Why? Previously it said you had nothing for me to solve inside it, right? The PEC is 0 inside, so it didn't have to solve it. But now that we put this air box around, it knows that it has to solve for the inside of the air box. That's why the 3D model is okay now. Now it says you don't have boundary excitations analysis set up. So let's take care of these. Let's save this. Oh, and for saving, sorry, for saving, you go Control S. Okay. ECE 1229. Okay. Okay. Now, I said that whenever we want this boundary or enclosing boundary to be not reflective and only absorb the radiation or act as if there is nothing there, you select it, you go right click on it, then you say assign boundary and radiation. This is the one, radiation. Can't really see it, but it says radiation. Yeah, that means that this dipole is going to radiate, and this box is only supposed to capture that radiation, nothing else. Yes.
If we define a much bigger box,
Yeah.
it would take more time.
Exactly. That's why you want to go with the minimum as possible and accurate as possible, right? As minimum, and at the still would make your simulation accurate. If you go less than lambda over 2 away from the boundaries of your geometry, then that would mean that the simulation is not going to be too accurate, because that's the minimum distance HFSS requires. And then at the same time, if you go very small good point, it takes much more time to mesh this geometry.
Smaller or
For bigger, it takes more time. For smaller, the results are not going to be accurate. Yeah. What else? So now, if
Is it the same as defining it as BEC,
the dipole,
the boundary of the box?
no. If you make it PEC, it would look like you put this dipole in a metallization box or metal box. What you want is radiation boundary. And so let's go back here, view. Now we want excitation. How do we excite this? One way to excite it is to define a lumped port. This is what HFSS calls it. A lumped port, it looks like a current, but has an impedance here. Since we already know the input impedance of the dipole, or even if you don't know, it doesn't matter actually, right? We can define a lumped port that goes from one PEC or one section of the dipole to another one with the current in this direction. And then you can assign Z to this lumped port. I would say this, it looks like an intrinsic resistance of the source. So I can define it to be 50 ohm, or as I know, the Z impedance of the dipole, I can define it 70 ohm, but it doesn't matter. I'll show you. So let's assign a lump port. Actually, a lump port is what you use in designing these antennas, like a patch antenna or microstrip line or things like that, basically. Most of it goes with that, unless you have like a waveguide. Are you familiar with horn antennas? Right? A horn antenna or an open-ended waveguide that looks like this. You have a rectangular cross section. This is, I assume you solved for this, the fields of this one. Then you would use a wave port, but lump port it is. So for a lump port, let's go to model. And left. Okay, so we want a lump port that goes from the center of the cylinder from this point to this point, from this point to this point. So what you need for a lump port is to be assigned to a surface. So let's go to draw. Again, I'll assign a surface here. Oh, so when you're trying to draw a surface here, it doesn't know where is the surface is lying. Is it in XY plane? Is it in XZ plane? By default, it would go to XY plane here. You can see the invisibility basically, but we want to go the surface or draw the surface in ZX plane, right? We want to go from this point to this point. So you would change this to XZ and then draw the surface from this point to this point. Now let's call this lump port. Now, again, we do the same thing. Even though the parameters might look right now. We want to parameterize it in case we change something, a parameter, then we can basically everything changes automatically. Okay, for this Lumport, I'm gonna go back to here since we only have white. I'll use this one. So the Lumport goes from the surface of this, the center of this cross section like this, goes from here to here, right? So it is lying in XZ direction basically. So what you want is to define it at y equal to 0, right? Y is always 0. You want to define it from minus r to r along x. And then for the z-axis, you want to go from minus g over 2 to g over 2. So this is what I'm going to do. In x direction, it depends on r dipole. For z, it goes from minus g dipole over 2. Y-axis, it doesn't even ask for y, the length in y direction, so leave it as it is. It would only say that what is the position, so you go to y here. Then in x, the size is 2r dipole, the diameter of the cylinder. Then in z, it's g dipole. Let's look at it, right? So it goes from one cylinder to another cylinder in the center. Now, if you look at it in this view, you'll see it. This is your lumper. You can even define it in the other direction, right? Put it along y-axis, doesn't matter. You can put it in a random direction, literally, it doesn't matter. As long as it goes from one cylinder to another. I would just say go along one of the planes or XZ or YZ because it's easier to parameterize it. Okay, so this is where the lumport going to be. We need to assign the lumport to it. So you go to right click on this surface, assign excitation, and then you say lumport here. Now, as I said, you can leave it as 50 ohm, and then, or you can change it to 70 ohm, doesn't matter. Leave it as 50 ohm for now. Then you have to define an integration line, which basically says like, where is the current going from one point to another? So we want to go from the center of the cylinder, one cylinder, to another one. Whenever it becomes this rectangular shape, that means that's the center of your line. Whenever it becomes square, that means that's the edge of your line. So that also helps you to find places. So you go from center of this one to the center of the other one. Next, and then you can renormalize it or do not normalize it, doesn't make any difference for now. Finish. Okay. Again, so we set the boundary is radiation. We set the excitation, which is a lumport. Now we need the setup. What is the solving, basically? So we want to say solve this geometry, this problem at 10 gigahertz, for example. So you go to analysis, add solution setup. You can go with either of these, but I would say go with advanced one so you have more control on the different properties. Then we say at 10 gigahertz, okay, at 10 gigahertz solve this problem. You can go with different multi-frequencies. Let's say you can say solve it at 10 gigahertz, 12, 13, 14, whatever you want. For us, a single frequency is okay. And for the rest of it, we put as frequency sweep. What it does is that whenever you define a single frequency, it would mesh that geometry at that frequency. Then for the rest of the frequency of your band, it would use the same mesh cells to solve the problem, right? So if you're not too far from that 10 gigahertz, there shouldn't be any problem for you. The same mesh would be okay for 15 gigahertz, for example. But if you want to solve it for 50 gigahertz, then obviously this is not a lambda over 2 at 50 gigahertz, right? So you need a different mesh cells or different meshing. That's why it really depends on what you're trying to go with. If your analysis is for a very broad band, it's good to have different frequencies in the band to solve it. But if it's for a narrow band, then one central frequency is okay, and the rest of it can be solved for in a frequency sweep, as I show you. So 10 gigahertz maximum number, I always set this to 30, for example, because if things are not converged, it can go. If you put this at 6 and the results are not converged, the simulation is going to stop anyway, right? So that's not good. You have to be careful. It might be okay to leave it at 6, but then you have to go manually check if your results are converged or not. If not, you have to go back and increase this. So in order to avoid this, I always put it as 30 or some large number, because that way it will continue till it's converged. The maximum delta S, this is 0.02. It's fine. You can leave it as it is. And refinement per pass 30%. You can change this to 40% if you want things to move faster. Like, what does that mean? That means that based on the delta, because this is the adaptive meshing, based on the delta that it found, it tries to refine the mesh to solve it again and see how it improves the results, right? Every pass, it goes, currently it says 30% improve the meshing, right? That's the default setting. Now, what happens if I change it to 40%? In 40%, sure, it tries to improve the number of mesh cells, or 40% of the mesh cells by 40%. But the problem is that the next pass is going to take more memory to solve it, right? Because now 40% of the mesh cells have changed. You've seen mesh cells, right? In RWG, for example, right? It's the same thing here. So you can, let me say what I mean by mesh cells. Let me go with a square, for example. Like this one. This is a square. HFSS, let's say, starts from a very easy case. Never starts from here, but it starts with RWG or triangular mesh number of mesh cells. In pass number 1, we might say, okay, I'll just consider 2 triangles. I would divide this square to 2 mesh cells, 2 triangles. Pass number 1 solves it. It sees, oh, things are not good, actually. Or actually, pass number 1 has no number. So pass number 1, it just solves it. Goes to pass number 2. Pass number 2, depending on this 30% or 40% or whatever number of mesh cells you indicate, it tries to go to, I don't know, 4 triangles like this. Now it calculates delta. It says this is the difference between the results of this and this are too much, right? So now it says, okay, something is off. Like, this is obviously not right yet, because if I change the number of mesh cells, or the number of mesh cells, things shouldn't be changing that much. This is the same geometry, right? Now, if you say only, for example, change 30% or improve 30%, since you only have 2 mesh cells, 30% of 2 is 0.6, right? 0.6. In pass number 2, it tries to only change one of actually these maximum. You will leave one of them as it is, the other one divides it to 2. Now, if you mention you can go to, I don't know, like 70%. Then the second pass, it tries to go to number of cells, four mesh cells. Now, what does that mean? That means that the difference is this. You had in pass 2, you either solve for 1, 2, 3 mesh cells or 1, 2, 3, 4 mesh cells. Now the difference, the geometry is the same, but it's trying to solve for 4 different regions, so this one takes more memory. You won't see this in a small structure like this, but try to imagine when you're trying to squeeze the simulation of a very large structure in HFSS. Now, even one more pass is very important for you. So again, you don't need to think about it. You can leave it as 30%, but no, less number means that less improvement, but at the same time, less memory. And a bigger number means faster improvement, but then more memory. Minimum number of passes here, you can say, I don't know, like 5 or something like that. Doesn't matter. But minimum converged passes. This is the important one. You don't want to have just one pass that is converged and then your simulation stops. Why not? Might be. Exactly. You might get lucky. It might be a coincidental convergence, right? So you want like at least 2 or 3 convergence so you know that everything is fine. Like literally, this is the answer. Okay. Now, the direct solver and iterative solver, I don't exactly know what they mean, but direct solver, iterative solver helps you improve things. Helps you save some memory when you're simulating, but at the same time, it needs more number of passes. So it solves faster and it requires less memory, but then you really need to check that things have converged. For now, for you guys, just leave it as direct solver. The rest of the tabs, don't change them. Well, this is a very advanced topic, so for advanced topics, you change it. Now, it suggests a frequency frequency sweep. At 10 gigahertz, it says if you go from 5 gigahertz to 15 gigahertz, that's a kind of like a normal band for something like this. You can change it. You can go from 1 gigahertz to 20 gigahertz, but keep in mind that you're only simulating at 10 gigahertz, as I said. If you want to go wider band, you want to change your frequency setup to have multiple frequencies there.
Where do you get the frequencies?
It just comes out automatically.
Okay.
After you're done with the setup, it shows up. Yeah. So 5 to 10, 15 gigahertz. Now, depending on like what is the resolution in the frequency that you want. For example, let's go to preview. It says, now this is almost 25 megahertz. This is too much. 25 megahertz is, I would say, is too much. So you can go to 101. Go with 100 megahertz, the resolution of the band. Now, so we have different types of sweep here. One of them is discrete. That means that you want the fields at each of these frequencies, okay? Whenever you want to design something at the very beginning, I would say don't go with this discrete because it takes more time. It tries to mesh it at all of these frequencies, solve it at all of these frequencies. So I wouldn't recommend discrete. For S parameter calculation or impedance calculation, interpolation always works fine. The fast one, again, you lose a lot of accuracy. So I would say stick with interpolation. If you go to discrete though, let's say you design this antenna for 10 gigahertz, you're interested to see if things are working at 10.4 or 10.5 gigahertz and 9.5 gigahertz as well, or how the pattern looks like at these two frequencies, okay? And I'll show you when this happens. Then you can just say, save the fields here, save the fields at these two frequencies for me. then you don't have to come back and simulate it again. When it solves for 10 gigahertz, it will solve for 9.5 and 10.5 gigahertz as well. I'll show you what I mean. Let's go with the very fast simulation. I don't want to mention too much here. So now we said, solve this problem at 10 gigahertz, simulate it from 5 to 15 gigahertz to see the S parameters. We want to see the S parameter or the input impedance of this dipole from 5 to 15. Now, if you want to see the radiation pattern, you have to go here, radiation. Whenever you have, only when you have a radiation boundary condition like this here, it allows you to make a radiation. Now we want to see the far field pattern, so you can put insert far field setup, infinite sphere, because we want to be infinitely away from the structure. Phi, for example, 100 minus 180 to 80. These are the things you can just literally change. I'll just go with this so that it will complete all the sphere. Okay. Let's see. So now we went through all of these different things that the HFSS needed to solve this problem. So this is done. Now you want to analyze it, you go to setup, right click on it and analyze. So first, it starts with solving this at 10 gigahertz. At 10 gigahertz, it goes past number 2, past number 2, past number 3, past number, we'll see. It has to go at least minimum of 5 passes. And then I'll show you how you can check on convergence. So first, it solves for 10 gigahertz, so you'll see the number of passes changing. After it converges at 10 gigahertz, it tries to solve it for different frequencies using interpolation. What HFSS does is use MPI, which is like a multi-core thing, to basically solve these frequencies from 5 to 15 gigahertz in parallel. So it would take much less time. Instead of solving 5, 5.1, 5.2, all of those frequencies that you mentioned. It solves it in parallel, so it goes much faster. Okay. Now it's almost done. It says cleaning simulation directories. Now it is started with different frequencies. It says solved 5 out of 101 frequencies, with 5 frequencies being solved in parallel. You see?
Yeah, how can we increase the parallel numbers? For example,
Yeah,
now it's 5, can we
I'll
increase
show
to
you.
10?
Yeah, I'll show you.
Also, for this one?
I don't know about actually, I don't know how you can increase the number of frequencies, but I'll show you how you can parallelize the parametric suite.
Also, for this one?
Yeah.
After we figure out the meshing size, can we explore the meshing? Just like Gmesh, can we export it?
I have to see. I know how you can plot the mesh, but I don't know.
Yeah,
You can export the mesh from this project to another project, right? I don't know if it exported as a mesh file for you.
Because if you can export, then we can use RWG to solve the current.
Yeah.
Also, another question is for example, like for this structure, we know after 5 passes, and we're gonna get conversion results. And the next time, can we directly go 4 and then 5 and then?
Yeah, you can. So basically, I'll show you.
So we ignore the first 3 parts, just directly go 4.
Yeah. So what you can do is you can assign or initialize the mesh.
Oh, so you increase the so you decrease the meshing size. You mean that?
Yes, basically that way. So for example, let's say it starts from that pass number 1, right? You can select this square and say apply some meshing to it, because you've already, for example, seen that when it converges, it actually has to go to, I don't know,
Yeah, yeah.
kind of like something like this.
Mhm.
Consider these triangles, right? You know, these triangles have a maximum size of like, I don't know, if this square size is L, the maximum mesh size is L over 4, for example.
Yeah.
Right?
Yeah,
So you can say that the initial mesh has to be smaller than this value so that it doesn't start from here. This mesh cell would be too large for the initial mesh setup.
Yeah, but the question is that we don't know it's lambda by 4 or lambda by what, right?
No, not lambda,
Yeah,
L.
L by 4, yeah.
Yeah, we don't know, but you
Yes.
can start from a smaller setting, like just like Gmesh, right? When you start things with Gmesh, you give it initial mesh setup, right? So you can do the same thing here. It might not be right, it still goes, right? It goes and tries to converge to the results by fine-tuning this mesh, but at least it doesn't start from that large mesh cells.
Yeah.
Okay, so this ended. Now let's look at the results. So you go here, results, solution data. Now we can look at different tabs. It says S11 is 1. Basically, everything is being reflected at 10 gigahertz. Sorry, this is as 5 gigahertz because we didn't design this for 5 gigahertz. We designed it for 10 gigahertz. And also we know at 10 gigahertz, yeah. So at 10 gigahertz, we have about 0.4 reflection coefficient, but that's considering 50 ohm. As you remember, S11, can we say ZL minus Z0, ZL plus Z0, right? If this is 70 ohm and you put this at 50 ohm, which we set up at the beginning, S11 is going to be large, right? We should have put this at 70 ohm. But let's say we don't know that. We don't know what is the input impedance. That's okay. Now convergence. Let's look at convergence. It says at the 6th pass, actually, the delta was smaller than the threshold that we defined. The target was to get 3 consecutive passes to converge, and we reached that. You can even plot this. Go to plot. You can see this is the target we set. And after pass number 4, 5, 6, all of them were below this threshold. So convergence is okay.
You use the delta 0.02?
Yes.
Okay.
Yeah. That was the default setting. We didn't
Oh,
change
okay.
it. Yeah. Okay. Now let's plot this 1 in different frequencies. So you go to results, right click on it, create modal solution data report, rectangular plot. Now you have all different things here. You can go S parameter, you can go Z parameter, everything. So S parameter in dB, set new report. So as we already knew, lambda over 2 for that length is actually going to be seen larger, right? Because we have these fringing fields from the dipole. So this dipole would look larger than lambda over 2 because of the fringing fields or edge effects, right? So instead of lambda over 2 at 10 gigahertz, it's going to be lambda over 2 at a lower frequency, right? Because when this L basically, now instead of like 15 millimeter, it's gonna look like, let's say 17 millimeter. If you consider that lambda over 2 and calculate this lambda and then frequency, since lambda went up, frequency goes down. So that's why instead of 10 gigahertz, we get it almost at 8.9 gigahertz. Let me enlarge this. Is it better? Okay. Enlarge these two. So now we are looking at S11 in dB, basically from 5 gigahertz to 15 gigahertz. dB S11, and then at 8.9, we get minus 16.5, right? Now, let's look at, okay, first, let's say you want to define the bandwidth on this antenna, right? How do we define the bandwidth? One criteria is when S11 is less than minus 10 dB. So let's go here. You can have even two markers here. So first one here, second one here, for example. Now M2 and M3, both of them are showing almost to minus 10 dB. So the frequency between these two is going to be where the S11 is less than minus 10 dB. So you can define this as the input impedance or S parameter bandwidth, which is delta X is 1.4 gigahertz, that means. So the bandwidth of this antenna is basically, you can say 1.4 gigahertz. Now let's go back to look at the input impedance of this antenna. You can go to Z parameter here, Z11, we know a real and imaginary. New report. So let's see, how does it look like at 10 gigahertz or 8.9 gigahertz? Does that make any difference? Okay. So the red one is the real part of the input impedance. And the real part of input impedance is actually, to go back and enlarge in this. So yeah, the red one is real of Z11, the green one is imaginary. The real part at 10 gigahertz is actually 105, right? The imaginary part is 28. Where does the imaginary part goes to 0? Let's look at it. The imaginary part goes to 0 around 9.2 almost. Yeah, between 9.2 and 9.1. Let's go to 9. Actually 9.2 is better. And then the real part is about 70, right? So basically this antenna around 70 input impedance and imaginary part of 0 is at 9.2. So if you go back here quickly, change this lump port to have 70 ohm. Now you see that it resonates at 9.1 gigahertz. I'm just going to quickly run this again to show you. Because we guessed the input impedance of a half-wave dipole wrongly. We said it's going to be 50 ohm, right? If we already knew, which we knew, but I wanted you to see that how the wrong calculation can lead to like these results.
When you change the 70, you just change the impedance to the normal?
The lump port. The lump port, I just changed it to 70 ohm here.
Okay.
Yeah.
So we wanted to resonate at 10 gigahertz.
Yes, we wanted to resonate at 10 gigahertz. I'll show you how you can basically bring it back to 10 gigahertz. Now, by changing this to 70 ohm, it's going to resonate around 9.1 or 9.2, because that's where the imaginary part was 0 and the real part was 70 ohm. The 50 ohm was completely wrong. We shouldn't, half-wave dipole is not this 50 ohm at resonance. We assign the material as PEC. The cylinder, you see here, he shows us PEC here. Yeah, you don't see it, right? That well. But yeah, the dipole, the material, I said it, like if you go here, dipole, I said the material as PEC here.
So if you're designing a patch, then we will assign the material as PVC.
For the top layer. Because this is a cylinder, it's a 3D structure, you basically have to assign materials to it. Only to the surfaces you can assign like,
So for the patch, I think we will give the specs of the copper,
mhm.
right? And for the ground, it's going to be PVC.
I would recommend to start with PC again for the simulation of the patch. Since we're running, well, we can stay here till 12. Let's decide if we want to continue staying. And if not, maybe we can go through, I have a couple of examples on planar structures like a patch. That would be more useful for your project. And then we don't have to go through all of these details again. So we can start with the patch tomorrow. If you, yeah. But we have the room till 12 if you want to stay. Now let's go back here. We have to update this since the results have changed. You can go right click on it and update. It's just solving. It hasn't finished solving, so. The same thing here. Update. Okay. Did that change?
What's the renormalize option do to the long port?
This one. Did I see one? Oh, it's because I didn't change it here. Yeah. Okay, now it works. Thank you. Yeah, basically this one would say that everything has to be, this would be the input impedance of the source. And you basically have to do, for S11, for example, you have to run this to understand it. Okay, yeah. So 7 ohm there too. Now, if you go here, it should be 9.1 almost. Yeah, exactly. So what we studied from the Z parameter, which was at 9.1 gigahertz, basically the input impedance had zero imaginary and 7 ohm real part. Now, if you go back to the long port and change all of that, you see that the S11 changes because S11 tries to calculate this based on Z0. And we assign Z0 to be 7 ohm. Now, that's important because when you try to calculate the bandwidth, like here, you go to your 10 minus 10 dB threshold, you see that now your bandwidth is actually 1.9 gigahertz, right? So if you didn't change the long port to 7 ohm, the bandwidth calculation was wrong, basically. Okay, now this is the S parameter, the input impedance, how you can study it. Now let's look at the radiation pattern of this dipole antenna. Now for the radiation pattern, we can go on this, basically, as you know, we can go on this plane, which is ZY plane. We can go on the XZ plane also, or you can plot it in 3D, let's say. Let's go with the 3D one for the first example. So you go to right click on the results, create far field report. And then for 3D, we go to 3D polar plot. We can plot gain, directivity. As you know, there is a difference. What's the difference between gain and directivity?
You have some loss efficiency.
Because of the efficiency. If the lump port wasn't matched to the input impedance of the dipole, your gain would be seen much less. Now let's look at directivity, for example. You can define the directivity for different components, theta and phi. For now, let's look at total in dB, and then new report. So this is basically like the donut shape that you would expect from a dipole. What is the directivity of a dipole, half-wave dipole?
About 1.5.
1.5,
1.5.
1.67.
Right? How much did you get? Maximum directivity, 2.7 here.
Oh.
Okay, right? So almost. We are looking at this result at 10 gigahertz, right? Where is the resonance happening? 9.1, right? How can I see this at 9.1 gigahertz? Because that's where the resonance happens. You can either go look at 9.1 gigahertz or try to tune this dipole at 10 gigahertz and then just look at the results at 10 gigahertz. I'll show you both of them. So this is the directivity. Something fun you can do is put this on the dipole itself. So you go right click on this and then show in modular window here. So now it shows you the plot or the 3D plot on the dipole. Again, if you want to create nice pictures for your report or try to imagine like how things are compared to your dipole, compared to your structure.
What did you click to get this view?
You go to directivity on this one, right click. The last option, show in modular window, there will be a check beside it.
Okay.
If I go up, you see that check, little check.
Yeah.
Yeah. Okay. Now you can even plot these or look at the plot in different planes like X, Y, or something like that. So let's go with, for example, let's look at the gain this time in dB. And so phi equal to 0 is the X, Z plane. Phi equal to 90 is Y, Z plane, right? Because we define phi from X to here, right? So either I can look at it in this plane and in this plane. Does it make a difference in the radiation pattern? No, right? Because the dipole is symmetric and the pattern looks like a donut like around it. But let's see if that's true. So 0 degree, and then the other one is 90 degree. Right, so this is the theta equal to 0 is here, because theta starts from here to here. Theta equal to 0 is here, where actually there is this null of this radiation pattern. So you have to null here, and then minus 80 and 80 are both this way here. So you go from 0 to here. You have two because I assigned from minus 80 to 80 for theta. So we go back from one null, we get to this null, and then go back to the second. Yeah. Okay. So we learned S parameter calculation, Z parameter input impedance, radiation pattern, directivity and gain. And now let's see if we want to change or optimize this dipole so that it would resonate at 10 gigahertz, right? So the problem is the length, right? The length seems larger. So we already know that if I make this smaller, since it's resonating in 9.4, 9.1, in order to make it resonate at 10, I have to make it smaller. As the frequency goes higher, the structure becomes smaller. That's a rule of EM, basically. So, but I don't know how much is smaller, right? Instead of try and error, I can set an parametric sweep in HFSS. Let's see how we can do that. So here we have something optimetrics, basically. You can right click on it, add parametric sweep. You can add LF dipole here. LF dipole, we calculated 15. So we don't have to go too far away. Maybe we can say start from 12, for example. We know it shouldn't go higher. So let's just stop at exactly 15 millimeter. 1 millimeter step. Then remember to add it. Okay, here, right? Now the table, it shows you what are the parameters that it's considering 12, 13, 14, 15. In general, it tries to run this parametric sweep for set of one that you have. Sometimes, let's say you have a dual band structure, right? You have a dual band antenna, for example. You have one element that looks like this, and then another element that looks like this on your structure. For example, this is hypothetical. This one is supposed to work at 10 gigahertz. This one is supposed to work at 15 gigahertz. And you have two different setups for that. Doesn't matter, like you can literally come back here and then add another setup here. Add another setup. So you can have multiple setup, multiple frequencies. Now, obviously, the length of this one, you want to see if this length, or you want to optimize this length to work at 10 gigahertz, not at 15 gigahertz. So both of these setups would actually show up. Let me go back here. L dipole 12. I should have added this before. Okay. Both of them would show up here, and you can just remove setup 2. Basically uncheck it here because you don't want to see the result of the lens or the effect of that lens at 15 gigahertz, for example. It will save you time, basically. Anyway, these are just advanced things. Now, okay, I want to see this parametric sweep and want to see its effect. So I go on parametric sweep, analyze it. Now I set up on my HFSS, I set up that so that it would parallelize this parametric sweep. You'll see it here, hopefully. Okay, yeah, you see it's solving 4 of them at the same time, 12, 13, 14. If you don't have this option that I show you, it would go consecutively. It will solve for one and then the next one. How do we set so that it would parallelize the parametric sweep? You go to tools, options, HPC and analysis options here. Edit. It says number of variations to distribute. This thing depends on the number of cores you have on your laptop, desktop, or whatever. But I set it at 10. And then the number of cores has to be 10. Then the RAM limit for me is 90%. Try to put it as not as 100% so that it wouldn't crash. But then 10 cores. If you want to, you see 10 is too much for your computer. Like I tried 20 and it's too much for my computer. So you can decrease it, but this is the setup. So if I had 10 parameters to sweep here, it would try to solve all 10 of them in parallel, basically. Yeah, but since I have 4, it will only solve for 4. The 3 remaining. Okay, now I want to see how does the S parameter look like for all of these different parameters, right? So one way, I go to the S parameter here, right click on it, modify the report. These different parameters would show up in the families tab. Now L dipole is a nominal, which is the 15 millimeter I set at the very beginning. I want to see the S parameter for all of these values. It hasn't solved it, but as soon as it solves it, it's going to update them on this report. Apply trace. Yeah, it's trying to solve. So this is for 15 millimeter. And it's, yeah, I can see, you can see these. It's just started for the others, you see. So hopefully, one of these parameters would make the dipole resonate at 10 millimeter. We could have gone by the ratio, like 15 millimeter works at 9.1 gigahertz, then how much is it for 10 gigahertz? But I wanted to show you like the parametric sweep, basically. What is it? 11, sir? So I guess we finish this one simulation, then we continue tomorrow because I don't think we can finish the patch if we start now till 12.
Yeah.
But please go home and try all of this on your own, because I know it was a lot, and then I recorded the session, so you can watch the video too.
I will probably take it on Zoom tomorrow. So log in on Zoom as well.
Okay. Yeah,
Parametric is still not working.
that's okay. Yeah, sure. It will be just like this today, though. Like, so if you need me to show you something better on Zoom, like, leave a message or something.
Okay.
Because, yeah, I have to move around.
The
It's,
screen will be shared, right?
yeah, the screen would be shared.
Just the blackboard part is you just have to write whatever.
Yeah, like my camera is directed at the blackboard,
Yeah.
but then it only shows obviously this one. You're ready to leave?
Yeah. Yeah, running on this computer or running on the server?
Understand.
Not sure if I missed something, but this runs the simulations that was 30 seconds.
Hmm?
I'm not sure if I set something up wrong, but I'm going to, they're finishing in like 30
Seconds?
Yeah.
Nice. Is it on your
And what-
laptop?
Yeah. I'm not sure if I just,
Yeah, on our
Laptop
server,
is
like, this is being run on our server, sometimes like other people are using it. so, yeah. Okay, so 13 millimeter was too short, probably 14 millimeter would work. Let's see. Yeah, this is not too difficult. I don't know what's going on with HFSS.
Slow.
But anyway, you can see, for example, for 13 millimeter now it showed up here, 15 millimeter is here, so probably 14 would go somewhere in the middle. So that's so L equal to 14 millimeter is basically your lambda over 2 at 10 gigahertz.
yeah, because I got
Did you get 14?
14 is the blue one, 13 is the green one. So it actually looks like 13 is a little bit closer.
Oh, really? Okay.
Something like 13.3 would be perfect.
Mm-hmm. Yeah. What is the difference though? Why our results are so different? So what's your resonance for 15 millimeter? What's that frequency?
Over down here.
You can put a marker, yeah.
9 gigahertz.
9, okay. Mine is almost 9.1. That's close. Anyway, I think that's it. I don't want you guys to wait here. Yeah. Stop share.